Welcome to part 2 of our notes on simple machines. So again, make sure you have the fill in a blank notes and they will help you. And you might wonder, why are they going to help you? Well, you won't have to put in all the words. It's fill in a blank. So that way, if you are at home and you have the fill in a blank notes, it'll be easier. But if you're trying to get caught up and you don't have the fill in a blank notes, you're more than welcome to write everything down. It'll just take you a little bit longer to do. So we're going to start by talking about our first of the 6 simple machines we talked about in part 1, and that is of the inclined plane. Now, do you use an inclined plane at all? Have you used an inclined plane at all today? If you're thinking no, well, think again. If you're thinking yes, are you thinking the same thing that I'm thinking about? How about the ramps? How did you get to your science class? Did you come down to ramps? Have you gone up the ramps at all today? If you've used the ramps to go up or down, you have used an inclined plane because the ramps are considered to be inclined planes. And back when the school was built, this was state of the art because elevators weren't as common. It was only much, much later that they put the elevator into the middle school. Otherwise, the ramps were how people got from one floor to the next floor to the next floor if they didn't want to use the stairs. So an inclined plane is basically a slanted surface used to raise an object. I use inclined planes all the time. Stairs are an example of an inclined plane. And stairs make life easier. Can you imagine having to go from floor to floor here in the middle school if we had to use a ladder? Have you ever tried to, say, put a lawnmower on the back of your pickup or the back of a truck? Or have you ever tried to load a car onto a trailer? More than likely, you have used an inclined plane. Now, can we find the mechanical advantage of an inclined plane? Absolutely. The mechanical advantage of an inclined plane, if you were to measure the length of the plane, so if we can measure from the bottom of the ramps all the way to the top of the ramps, and then if we could divide that by its height, that's how we find an MA of a ramp. So we could actually do this. If we wanted to, we could go out into the hall, we could measure how long the ramps are. We can measure the height of the ramp, and then we could actually calculate the mechanical advantage. How much easier does it make the work feel? Again, it's not actually producing less work, it just makes the work feel easier. The amount of work is actually the same, it's just that there's less effort that you have to put into it. You might wonder, okay, so how can we put more effort into it or less effort into it? Well, the trade-off is distance. Again, remember, work equals force times distance. If you want the force to seem easier, the trade-off is you have to increase the amount of distance. So when you look at the ramps, are our ramps here in the middle school, are they shorter than the stairs or longer than the stairs? And what I mean, if we took a tape measure and measure from the bottom of the stairs and we went kitty corner slant up to the top of the stairs, they're not as long as the ramps. The ramps are really long. So what's the trade-off? Distance. And that's how it makes it have a larger MA. So work done will be the same whether it's a straight up or an inclined plane. So if we were to pick a box up and we were to lift it straight up over our head, and if we were to pass it to someone on the floor above us, the amount of work done there is the exact same if we were to use the ramps to go up to the floor above us. The trade-off? Well, if I'm going to hand that box to the floor above me, it's what, 10 feet? Now, I know we have the ceiling tiles, but you go above the ceiling tiles, there's a couple more feet. So it might be 10, 12 feet to the floor above me. But think about it, we'd not only have to go up one set of ramps, we'd have to go up 2 sets of ramps. That's a long distance. So the amount of work that would be that it would take to move that box up one floor is the same. Now, in the first instance where I'm just taking it and I'm picking it up and I'm handing it, say, to someone on the next floor or putting it on the next floor, what's happening there? A lot of force. Not a lot of distance, a lot of force. Now, if I was to take that same box and if I was to move it up the ramp and I'd have to go from the first floor to the second and up to the third, and if you're watching this video and you're not from Baraboo, that probably doesn't make sense, but we kind of have a split level school. So if we were to calculate that, the amount of work is the same, but yet it would seem a lot easier. The trade-off is we have a lot more distance to travel. So remember, work equals force times distance. When lifting straight up, the distance is small, but more effort. Using a plane, the distance is longer, and again, an inclined plane. The distance is longer, but the force is less. So a slide. Now, don't look at this kid. He's actually going up the wrong side of the slide. Now, have you ever been yelled at for doing that? I can remember as a kid always wanting to go up the wrong side and having people yell at me, oh, it's dangerous. You're going to fall. You're going to hurt someone. But I did it anyway. But that's an inclined plane. Or when you have this pickup, when they have hydraulics and they pick up to one end. So you might have gravel. Sometimes they'll deliver lumber like this, and then they'll just pick it up and the lumber will slide right off onto your driveway or wherever they're dropping it off. That's an inclined plane. So the next one we're going to talk about, the next simple machine, is called a lever. And this person right here is using a lever. In its simplest form, a lever is a stick that is free to pivot or move back and forth at a fixed point. And that fixed point is a fulcrum. So if you've ever taken, say, a branch and you wedged it underneath something and then you put like a rock in the middle and you try to use it to pick up something, that is, well, basically it's a lever. The easiest way to remember the difference in the different types of levers that we're going to talk about is where is the effort, where's the resistance, and where is the fulcrum. So let's take a look at this a little bit closer. So remember, the effort force is the force you exert on a lever. It's where the effort is put into it. It's where the force is put on a lever. The fulcrum is the pivot point. And we're going to look at 3 different types of levers. And you're going to be able to see where it pivots for each one of those. And again, the resistance. Sometimes this is called the load. So if you see it on a worksheet and it says the load, this is the same as the resistance. This is the force a lever exerts on the resisting object. So there's 3 classes of lever. And they, you might say, well, what do you mean 3 different class of levers? We're going to get into that. But the type of class of lever, the type of lever depends on the position of the fulcrum in relationship to the effort and resistance arm of the lever. So here's a first class lever, and this is the easiest to remember. I never forget what a first class lever is. The first class lever is the fulcrum is between the effort force and the resistance force. So when we look in this, well, what do you guys know what this is? It's a teeter-totter. So the fulcrum of the teeter-totter is right in the middle. You've got effort on one side, you got resistance on the other side. The fulcrum is in the middle. So whenever you have a lever where the fulcrum's in the middle, it's automatically a first class lever. So again, we see the effort being applied by someone's hand on one side. If you got the fulcrum in the middle, and then you have the load or the resistance on the other side. Fulcrum's in the middle, first class lever. So here, first class lever. Here we see well, you guys know what this is. I don't know if you guys even know what this would be down here. This would be for a well, where it's going to pivot where you have the bolt, next to the person's hand. So that would be your fulcrum. So you have your pivot point, and then you're going to raise it up, and then it's going to pull up on the other side, and that will open up the well. So again, fulcrum's in the middle, resistance on one side, effort on the other side. Anytime you have the fulcrum in the middle, first class lever. Now, second class lever. Here the resistance is between the effort and the fulcrum. So the example is a nutcracker here, and my grandpa used this all the time because he used to collect all the walnuts, and he would use this to crack the shells open. We'd use the walnuts for baking. So this would be an example. Now notice where the fulcrum is. The fulcrum no longer is in the middle. The fulcrum here is on the far right. You can see the bolt that's going through it. And you apply the effort on one side, but the resistance is in the middle here. So here it's going to look different. The fulcrum is not in the middle anymore. So here the fulcrum is on the far right. The effort is in the far left. And the load or the resistance is in the middle. So we're going to have to remember this. The effort's on one side. You have your load in the middle. The fulcrum's on the other side. This is a second class lever. A wheelbarrow. Well, the wheel is where you're going to have your fulcrum. That's where it pivots. Now, where do you hold on to it? You hold on to the other end. That's where you apply the effort. Where's the resistance or where's the load? Well, it's in the middle. So wheelbarrow is an excellent example of a second-class lever. Look at a car door. You apply the effort on the handle. The fulcrum is on the far end, and the resistance or the weight of it is in the middle. So both of those are examples of second-class levers. Sometimes what I like to do is I like to remember the word free. You might say, free, where did you get that from? Well, look up above. The F is the fulcrum, the R is the resistance, the E is the effort. Free. You might be saying, well, free is spelled with 2 E's. Well, I'll just pretend for a second it only has 1 E. So second-class lever, free. Now, the third type of lever is called a third-class lever. So you have a first, second, and third. Here, the effort is between the fulcrum and the resistance. So again, first-class lever, fulcrum's in the middle. When we go back to a second-class lever, the resistance is in the middle. So a third-class lever, the effort is in the middle. And tweezers are a perfect example. Look, you have the fulcrum on one side, you have the resistance on the other end. And where do you apply the effort? In the middle. Same thing with a baseball bat. The resistance is where the baseball bat hits the baseball, or the softball if it's a softball bat. The fulcrum will actually be your wrist as they're pivoting and spinning as you're trying to hit the ball with the bat. And the effort is applied by your hands. So again, your effort is in the middle, the fulcrum is on one side, the resistance is on the other side. Now again, here you see it, effort's in the middle. Second class lever, load or resistance is in the middle. First class lever, fulcrum's in the middle. So here, how can we remember that? What's a mnemonic device? Well, look at it here. FER, F-E-R. So free was the other one if you want to remember FER. And again, I know you don't spell, typically, you don't spell FER, F-E-R, it's F-U-R, but you could do it this way. Now, please don't go the other way. If you go the other way, it's R-E-F, and I don't want people to think of ref being third-class levers. Refs are always first class in my book. So think of FER as in fur. Yeah, I don't know if you want to think of fur from a rabbit, but FER is a third-class lever, free is a second-class lever, and a first-class lever, I just remember the fulcrum's in the middle. So when you look down below, a mouse trap, again, you have your fulcrum, the effort's in the middle, the resistance is on the end. So again, throwing a baseball would be an example of a third-class lever, where you have your resistance in the middle, you have your, well, throwing the base would actually be the fulcrum would be your shoulder, and then the effort's in the middle, it's your, what's your arm, your muscles that are applying it. A hockey stick. A hockey stick would actually be a third-class lever, where you have your wrists that are moving it, or your shoulders, depending on how is it a slap shot, how are you using the stick. So a hockey stick would be another example of a third-class lever, where the resistance is going to be down where the hockey stick hits the puck. And your shoulders, your wrists are where it turns, that's your fulcrum. And then you apply the effort in the middle. Now, how do you find the mechanical advantage of a lever? Well, the MA is simply the effort arm length divided by the resistance arm length. So if you have the measurements, it's the effort arm length divided by the resistance arm length. So you would just have to measure each of those and then just divide them. So simple division. So use the calculator to do that. Again, effort arm length divided by resistance arm length. Now let's take a little quiz here. So what class of lever is this pry bar? Now if you use it as an actual pry bar, what do you think it would be? So let's just say, for example, on the far right here, you can see where you would pick up the nail. Well, if that's where you're picking up the nail, this is where it's going to pivot right here. So that's your fulcrum. So it's going to pivot where it curves. And if you apply the effort. Now, you could turn it around and you could use the crowbar the other way. It just depends on what you're using the pry bar for. So do you think this would be a first-class lever, second-class lever, or a third-class lever? Well, if you said that would be a first class lever. Well, what are you using the pry bar or the crowbar for? If you're using it to pound a nail, it would actually be a third class. However, if you're using it to actually use it as a pry bar, if you said it's going to be a first class lever, you're absolutely right. So again, if you thought it was going to be an A, yeah, well, you're kind of right, but not if you use it normally the way it should be used. Now, have you ever used a pry bar to pound a nail in? Most people don't do this. So if you said A, well, you technically could use it as a third class lever, but it's not likely. Here, the fulcrum is where? In the person's wrist. And if it's a third class lever, you had fulcrum, you had the effort would be applied where the person's hand is on it, and then you have the resistance where it's hitting the nail. Now, if you wanted to use it as a third class lever, could you? Or a second class lever, could you? Where you have free, where you have fulcrum, then you have what? Free. So you have fulcrum. What's the R stand for? Resistance. So is the resistance here in the middle? Yep. And then free. So the last letter is E. Where's your effort? Well, you can't see it in the picture, but the effort's off to the far left. That's where they're picking out. So if you use the pry bar like this, and then there's usually a slot for a nail in like that, then it would actually be a a second class lever, not a third class lever. So a third class lever I remember as being FER, F-E-R. Second class is free, F-R-E. Fulcrum, resistance, and effort. So if you used it like this, and you said it was going to be a second class lever, well, technically you're correct. It could be a second class lever. Now this does conclude part 2 of our series of videos on simple machines. Again, as always, if you have questions about anything you saw in the video, make sure you ask your teachers.